Hi, good morning, and welcome to the second day of the main conference of NetSci 2017. It's my pleasure to introduce to you today our second keynote speaker, Steve Borgatti. Steve has 30 years of experience working in the social network analysis field. He has quite a body of research, and in particular, theorizing, defining measurements, conceptualizing concepts that are pretty central to the core of social network analysis, such as centrality, cores and peripheries, and positional analysis. And he is in particular interested in organizational analysis. Steve has a sort of a roundabout way that he got here. He started out as an anthropologist, moved into the mathematical social sciences, and then moved into organizational studies. And he's now the Paul Shalgreen Endowed Chair at the University of Kentucky at the Gatton College of Business and Economics. Did I say that correctly? Okay, great. And he is also the founder of SOCNet, which is a listserv that I believe many of you are on. So if you are on that, you have Steve to thank for founding that. He is with the Link Center for Social Network Analysis, also at the University of Kentucky as well. He is the past and current president of the International Network of Social Network Analysts, which hosts the Sunbelt Network Conference. And he has received from them the Zimmel Award, a Lifetime Achievement Award there, and also the Richards Award, which is a Software Achievement Award as well from Sunbelt. We are just really thrilled to have Steve here to represent the social network analysis field, and I'm really looking forward to hearing the content of his talk. I think this is important for many of us. Centrality in three ways, and a concept in search of a definition. So thank you.
Thanks, Sam. Can you hear me? Okay, great. So thank you for inviting me to this. I have not been before. And due to family circumstances, I've had to squish down my visit to basically my talk, and then I leave, which is really unfortunate because last night I was having a very nice martini and reading the program and thinking, wow, this would be a really fun conference to be at. But this time I can't do it. I'm talking about centrality, and let me find my clicking operation here. And centrality is one of those areas that is great to work in because it's so easy to construct a centrality measure. And if it makes it, and it's easy to get it published, and if it makes it, if people use it, you can have a measure named after you. You can have like Borgatti's B or something. So there's always that hope. And there's not exactly high standards for what constitutes a centrality measure. You can produce just about anything and call it a centrality measure as long as it's node level. So we've obviously done things backwards. We've put the cart before the horse in the sense that very few people have any clear idea of what a centrality measure is, but they have written many of them. Right? And so what I want to do is to sort of put out some guidelines as to what it could be, how you might define it, what should they do, is there any help that we can provide, and when to use a centrality measure over another. So typically, what people say is, well, a centrality measure is a measure of importance of a node. That's the most common statement. They might introduce their own centrality measure with more sort of figurative, specific language. It might be prominence, influence, status, prestige, power, advantage, social capital. And I just reviewed a paper yesterday that created a new centrality measure, and they called it the Shared Leadership Index. Okay, so that now there's leadership. I would point out that the word structural, that's one little bit of information that actually more or less holds. By structural is meant that the measure depends on the pattern of ties. It is dependent on the structure of the network only. You don't bring in qualities of the people such as their gender or their race or so on. It's about the network. So that narrows it down slightly. Now, there have been a few attempts to define what centrality is. And most of these attempts basically are of the character of saying, look, if it's going to be a centrality measure, it ought to fulfill certain kinds of conditions. One of those that everybody agrees on is that isomorphic nodes should have the same scores. And so if we look at, for example, node B, if I point at B here, you don't see it there. But it's very nice for me. The product improvement idea, by the way, for anybody here, I point to any screen and it shows up on all screens. So if you look at B and G and I and D, they are automorphically equivalent. If you were to lose the labels on the graph and pick it up and flip it around in multiple different ways and then plop it back onto the screen, you wouldn't be able to tell which one is B, which one is D, which one is G, and which one is I. The same is true of the red nodes, and the same is true of the blue nodes, right? And you can see that these are the symmetries of the graph. You could flip it left to right, you could flip it upside down, you could do 2 flips, and so on. So obviously, if centrality is a structural measure, then it must come up with the same value for structurally identical nodes. So that's a minimum condition. The opposite isn't true, of course, because the opposite would mean that if 2 nodes have the same betweenness value, that they are structurally isomorphic. And that would mean that we would have just solved a great problem where an NP problem has been shown to be on the order of P, if that means anything to you. Another idea is the idea of Sabidusi. Sabidusi suggests 5 different criteria for what constitutes a well-formed centrality measure. They are things like the centrality of a node is always improved if you add a tie to that node. And the centrality of a node is never hurt by adding a tie somewhere else in the network, not directly connected. It's a logical sort of axiomatic approach, which is great. The big problem is that only his measure survives his tests. So kind of rigged in a certain direction. Freeman said, well, if it's a centrality measure, then if you give it a star graph like this one, that node that's in the middle of the star must get the highest centrality score possible. I don't mean just highest among those 5, but I mean that there is no other graph of that size that would yield a node with a centrality score as high as that number 1. This is nice too, but again, the problem is that it fails for a very large number of measures that none of us want to exclude because they work well. We like them. And in any case, Sabidusi, Freeman, none of these measures actually define centrality. They just say, well, it can't have that property or can't do that. So, and this is just an example at the very top here of a star graph in which we have a cat's centrality measure. Actually, this is a beta centrality measure right there. And then if we add a tie to it, that one actually increases. So it just goes against the whole star thing. So what I'm going to do here is just present 3 perspectives on centrality that I think at least move toward providing a serious definition of centrality. They don't actually solve the problem, as you'll see, but they get somewhere. So before we get started, a few terms and assumptions. I'm going to use a walk to mean any traversal through the network. So by a traversal, I mean that you could start, say, somewhere at A, you could go to C, you could go to E, you could go to H, but in a walk, you could go from A to C to A to C to D to C to A to B. There's no restrictions. Okay? By a trail, I mean a walk in which you can revisit nodes, but you can't revisit lines. All right? And by a path, I mean a trail in which you can't revisit nodes. And then finally, at the sort of most detailed level, there is the geodesic, which is a path that happens to also be a shortest path, so that there's no shorter way of getting from A to B or whatever. And just for convenience, I'm going to assume non-reflexive, undirected graphs. That doesn't change anything, but it makes it easier to explain stuff. So I'm going to start with the involvement approach, or what I call the involvement approach. It's one way of defining things. Is someone doing some kind of Buddhist thing? Because I do feel more centered now. Um, so the idea here is that what centrality does is that it measures a node's involvement in the walk structure of a network. So there's a walk structure in any network that we can define, we can write down. And the more a node is involved in that structure, the more central it is. And various centrality measures differ from each other in sort of what aspects of that walk structure they consider. So to see this, let's just look at some well-known measures of centrality. Starting with degree. Degree is usually defined as the number of ties that a node has, although there are other definitions. And for my purposes, it's convenient to remind you that a tie is just a path of length 1. It's a really short path. So what degree is that it counts the number of really short paths that emanate from a node. And again, I say emanate. It could be that terminate. I'm not going to consider direction here. It'll all be the same anyway. The emanation and termination indicates a kind of a role for the node. And that role I call measures that have this property of counting up paths that leave a node as being radial measures. I'll contrast that with medial measures in a moment. And degree is one of these measures that has lots of variants that are published. For example, as far back as 1965, Sage, studying primates, decides that the measure of centrality that really matters to him is counting all paths of length 2 that emanate from a node. Closeness, very similarly defined. We replace the adjacency matrix with the distance matrix, and then we sum across the rows to get the row sums there. Or we could just as easily take the average. And in fact, the average is a little easier to think about. The measure is only considering shortest paths. It records a different property of paths. It's not counting them up now. It's just saying what's their length, what's their typical length. And again, the role of the node is the endpoint. It's like, of all the paths that leave me, on average, how long are they? Right? So I'm just building up variables that each of these measures differs on by 1 or 2 things. There's random walk betweenness. So we can think about this in terms of Markov processes, where it would be called mean first passage time. And we're just talking about a random walk through the network. It can go anywhere. It's an unrestricted walk. It's not a geodesic anymore, like the previous one. It's random. And we can calculate, by making each node an absorbing a state in a Markov process, we can calculate the mean first time of arrival of a token moving through the network. That's not difficult to do. And we can see that it looks at unrestricted walks. We can see that it records the length of the walks. It's the time until arrival. Again, we're looking at these radial things. It's the number of paths or walks emanating from the node. Let's go betweenness. These are all sort of the famous ones. So let's just, we'll do those. So betweenness is loosely how often a node lies between 2 other nodes along a good path. And by a good path, I mean a geodesic path. So for example, X here is in a good position in the sense that S needs to go through X to reach M. In fact, that's the only way to get to M. Is that true? That's not true at all. There are other ways to do it. You can go from S to Q to T to X to M. Every single path, though, that you could take always goes through X. So X controls all the gateways to M. But the measure only looks at shortest paths in any case. So there's only one shortest path here. From S to T, there are 2 shortest paths, one through X and one through Q. And what the measure does is that it says, well, we'll give each of them a ½ point for being both along shortest paths between these. So obviously, this is a measure that looks at shortest paths only. It's a count. It's not looking at the length of the path. It sort of defines that away. I'm only looking at short path, but it doesn't care how long the short path is. It's counting them up. It's a frequency measure. And rather than counting the number of paths that are emanating from the node, it's the ones that go through the node. It's the number of times that the node that you're measuring is in the interior of a path. So I call these medial measures. There's a lot of different variants of betweenness. There's flow betweenness, which we'll talk about more later. There's a random walk version of betweenness. Again, it's pretty clear what it does. It counts random walks, so unrestricted walks. So let's try to wrap this up then. Oh, no, we're not. We still have one more slide. I did that for you guys. I wanted to hurry it up so we're not late and stuff, but this presentation has its own mind. So eigenvector centrality, very sort of nice measure. It has the property that, as you can see here, that a node's centrality is proportional to the sum of the centralities of one's friends, which is kind of a cute concept. It can also be thought of in different ways. And this is the way that actually Hubble first wrote it down in, I don't know, in the 60s. And through rearranging terms and so on, what we can find is that we can rewrite eigenvector as this inverted matrix times a column vector of ones. The column vector of ones simply constructs the row sums of this matrix. So if we look at that matrix, under the right conditions, if beta is smaller than 1 over lambda, the largest eigenvector, then it's equal to this expansion here. And where these are the matrix powers, and A3, for example, tells you the number of walks of exactly length 3 that go from any node to any other node. And A to the 5th would tell you the number of walks of exactly length 5 that go from any node to any other node. So this infinite sum here is simply giving you the total number of walks from any node to any other node, weighted inversely. That's what the B's come in to do. Imagine that they're smaller than 1, weighted inversely by their length. And then we take the row sums of that. So the measure basically counts up the total number of walks that emanate from a node, weighted inversely by length. Okay, so now I'm thinking, you've seen enough individual measures. You've seen what the variables are that I'm pulling out of them. So it's time to create a little typology. And the typology here is a 3-dimensional table where across the top here we have the different kinds of traversals that are allowed, that the measure pays attention to. Within the rows here are what aspect of those traversals we care about. Is it their length or their frequency? And finally, the role of the node in all of this, which is whether it's a radial or a medial. Radial meaning the paths emanate from it, or the medial, the path goes through it. So this classification would seem to classify all centrality measures. There's a few where we have to realize that they combine both length and frequency, but that's okay. So that's one way of thinking about what centrality measures do. They measure the involvement in the graph structure, in the walk structure of the graph. Another approach that is based on the same idea, it takes that same notion of involvement and switches it to maybe the word contribution. It's contribution to some aspect of the network, and it's called the induced centrality approach, and it's one that I'm very excited about. So the way it works is you start by picking a graph invariant. And what I mean by a graph invariant is any property that is purely structural of a network that depends only on the pattern of ties. So for example, you could count the number of transitive triples, or you could count the average path length between all pairs of nodes, or the number of people who are separated by exactly 2 links. Any statistic like that that describes the entire network, and there's a single number for the whole network. And of course, we can have things like small worldness, scale freeness, and so on. Now, very simply, once we've calculated the graph invariant, we remove a node whose centrality we want to measure, we recalculate the invariant, and we take the difference. And that difference is the contribution that that node made to that overall graph invariant. And you just repeat the process for each node sequentially. It turns out that many of the measures that we discuss are induced centrality measures. So degree is one. It's very trivial, but degree is one. If you think about this network here, and we're measuring the centrality of D, and let's make the graph invariant here be the number of edges in the graph. Then, per our process, we delete D, and we count up the number of edges in the new graph. There's only 3 of them. There used to be 6 of them. So 6 minus 3 is 3. And that's the induced centrality of D. And of course, it's also the degree of D. Because when you remove a node, you remove the ties adjacent to it or incident on it. And so degree almost trivially, well, not, it isn't almost trivial. It trivially is an induced centrality measure. Flow betweenness is an induced centrality measure. Actually, in the original paper that I wrote with Lynn Freeman, the way we defined it was as an induced centrality measure. We actually compute the maximum flow, and here I'm talking about maximum flow in the sense of Ford and Fulkerson and Menger and those kinds of things, and looking at the total flow from every node to every node, and then removing a node and seeing how much less can flow throughout the whole network now that that node is not there, and do that separately for each node. So that's clearly an induced centrality by construction. There is the question, I could show you several others, but the question comes up eventually, so is this an alternative definition of centrality measures? Do all measures satisfy this criterion? Can they all be described as an induced centrality measure? And here it's interesting to look at the case of closeness. Closeness can be defined on this network over here. So here's our original network G, and take a look at node A and node B. Node B is a little bit more central in the network, and node B has a centrality of 13. Node A has a closeness centrality of 14. And as you know, it's a reverse measure, so the 13 is better than the 14. Now, how do we get to that as an induced centrality? We need to figure out what is the graph invariant that we could use that would we would get those numbers. It turns out we don't even have to think about which the graph invariant is, because in order to do this induced centrality, we're going to have to, at some point, we're going to have to delete A from the network. And we're going to, that's shown here, and we're going to get a network that looks like this, where A is not there. It should be there, but it's not. And we're also going to have to delete B, and B should be right here, and it's not. And the thing is that when you do that, and then you compare these 2 graphs, is you realize the 2 graphs are isomorphic. They're absolutely identical. So any graph invariant that we would calculate here is going to give the same score for A and B because they leave the same residual graph. And yet we know that they're not equally central, so that means that closest centrality cannot be an induced centrality. So it's outside of that set. It's kind of like, I've just shown P not equal to NP for those of you computer scientists. So we've got the set of measures here that can be calculated using the involvement approach, and we have closeness here that is only in that set. A number of measures are in both sets, and this is the set of induced centralities, and actually we've not looked over here to see what induced centralities cannot be described using the method that I talked about earlier. Now, I've actually made my point at this point, but I can't help but tell you something fun about these glass invariants. There's just cool things you can do with them. So here's a special class of graph invariant induced centralities. Suppose you take any off-the-shelf measure of centrality, betweenness. Okay, we're just going to use betweenness as the example. And that's a node-level statistic, but we're going to sum it up across all the nodes to get a single number that is a signature for the whole graph. Okay, that is the graph invariant that describes the entire graph. So we get the betweenness for each node. We sum them up. This becomes our graph invariant. Now we remove a node. We recalculate betweenness for every node, sum it up, and compare it to the previous sum. And the difference is going to be our induced centrality. So really what we're doing is kind of a decomposition, because take a look at this equation here. Or actually, I sort of prefer it written this way. You have the direct centrality, which is the centrality that you took off the shelf. That's the betweenness centrality with which we measured every node. And then we summed it up to get the graph invariant. And so we have a person's actual betweenness centrality. Then we do the process of removing it from the network and recalculating the sum of betweennesses. And that gives us our induced centrality, which in this case I'm going to call total centrality. And these numbers need not be the same. The difference between them is an indirect centrality that a node somehow contributes to. So let's look at an example. In the case of betweenness, I've written the process a few times here. It's the same process. And what we're going to get is an induced value by dropping each node and seeing what the sum of betweennesses is after dropping it. And we have the betweenness as Freeman would have calculated it. And then we could subtract these two in order to get this indirect bit, this exogenous bit. And here's an example that might make this somewhat clear. It's the classic Paget and Ansel marriage ties among Florentine families. And you see the Medici over here. And in the table, what we see is sorted. We have each node. The endo column is their actual betweenness. That's the betweenness that any network package would produce. We then then we sum those all up to get the invariant. Then we remove the Medici. We recalculate betweenness for every node, and then we sum it all up, and the difference is 73. So the total betweenness that is being contributed by the Medici is 73. Their direct score of betweenness is 48. The difference between those is 25. The 25 is the amount of betweenness that the Medici are contributing to the rest of the network, not just through their direct efforts. It's like by being there, they make other people more central, 25 points worth. Some of them, like Salviati, even more, their own betweenness is fairly modest, but if you remove Salviati from the network, you get a 57-point difference, which means that what they're contributing to other people's, to the sum of all centralities, is 44 points. And you can see that by looking at where they are over here. Both the Medici and Salviati have this property that the Medici have their own betweenness, but if you take them out, Salviati no longer has betweenness. The only reason Salviati has betweenness is because the Medici are here to connect to the rest of the world, and Pazzi can go through Salviati to reach the rest of the world. But if you take out the Medici, Salviati is no longer a high betweenness node. So you can see how one contributes to the other. The really cool thing, in my opinion, is that you can even have negative values here. So here's the Ridolfi, and they have a betweenness centrality of 10. If you remove them from the whole network and resum up all the betweennesses, the sum is actually smaller than their direct contribution, which means, so the difference is -1, which means that the net effect of them being in the network is to reduce other people's centrality. Okay? They're like, I don't know, a spoiler of some kind, the cooler at the table. So I think that's kind of a cool concept, how much you create centrality for others. So just for fun, I did an empirical example. I used data from Ron Burt because that makes this all the more legitimate, because Ron Burt's a big name. We got 300 employees. We have compensation data. We've got supervisor's evaluation. We have lots of control variables. And we have a dependent variable, which is lagged compensation expressed as z-scores. So I run a regression. And in my regression, I include all these control variables, what level of manager you are, how old you are, seniority in the organization, whether you're in the Singapore office, whether you're male or female. And I find that exogenous betweenness, the amount of betweenness that you contribute to the rest of the world above and beyond your direct contribution, is significantly negatively related to compensation. What this means is the more you help others become central, the worse it gets for you. The worse you are recognized, the worse your salary is. Which somehow makes some kind of sense, you know, an image of slimy corporate snakes competing with each other, and it suggests that there is nothing good in helping others here. It might be good for the company as a whole, but it's not good for you. You heard it here first. So, one last approach. 15. So that doesn't say 3:17 in the afternoon. It's counting down. I have 15 minutes left. This is very cool. Okay. So here's a different approach. And the approach is this. We've been considering, particularly in the very first one, we've been considering the involvement of the node in the walk structure. And the walk structure is really about all the possible traversals that you can make through the network. And a traversal is something which could be a flow, right? It could be information flowing through the network. It could be a disease flowing through the network. So why don't we focus on those flows? Think about the process that we're studying as flows. Because fundamentally, it's not so much that centrality by itself affects anything. It's more like if you're well positioned, then maybe you acquire bits of information that you can exploit to then do the right thing, that you can help a friend with, that whatever, that provides value. So let's look at the flows. And closeness centrality is kind of a too simple one, but if you have good closeness centrality, that means that you are separated from the rest of the network by few intermediaries. The paths are short from you to everyone else, which means that things reach you quickly, which means that, well, if it's a virus, it means that you might get it before there's a cure for it, but if it's gossip, it might be very useful. If it's a new joke, it's a lot more fun to tell a new joke that no one's ever heard than to tell the joke that everyone's already heard, right? So it turns out that, in fact, it does map onto exactly the mean first passage time for a flow process that has a very specific regime. And that regime is that everything flowing through the network flows across shortest paths. Highly unrealistic. What in the world flows across shortest path? Even FedEx doesn't take the shortest path. And it counts for FedEx, right? Distance matters, and the number of handoffs matter, and so on. But it's a little bit unlikely. But let's just make it clear that closeness it provides an exact point estimate of the mean expected time until arrival of something under the conditions where things flow along shortest paths. So maybe we can look at other kinds of flow regimes. Betweenness. Betweenness is another example. Betweenness has all the different interpretations that we normally give it about power because you're between two others and you can control the flow of information and so on. But from a point of view of a flow process, what betweenness does is it counts how often something flows over a given node as it goes somewhere else. And in fact, it's a perfect point. That formula is a point estimate of the expected amount of stuff that flows over a given node under a flow regime in which A, things travel along shortest paths, and B, when there are equally shortest paths, it chooses uniformly at random among them. Okay, it just flips a coin. Under those conditions, that works perfectly. Degree as a flow outcome. Degree also works. If you assume that something is moving through the network in a random walk, so it's not geodesics now, but it's walks, and it's unrestricted, then it's easy to show that in the long term, the number of times that something touches a node on its way somewhere is proportional to the degree of that node. Right? This is just a really ancient result in Markov chain theory. So again, it's an outcome of a flow outcome. It gives the frequency with which something touches a node in a certain process. But the unrestricted walk is not one that we commonly run into in processes that we care about, and shortest path is definitely not one. So it would be useful to take a look at, well, what kinds of flow regimes do we care about? Let's take a used book. I read the book, I hate to throw it away, I give it to somebody else to read. Right? They read the book, they hate to throw it away, they give it to somebody else. At some point, that book might come back to me, because whoever is reading it now has no idea that I have ever read the book. But now what do I do with it? Well, typically I give it to another friend. I don't give it to the same friend that I gave it to before, right? Unless I have Alzheimer's, I'm really old, or you're a member of one of my family, which tells the same stories and does the same things over and over again with the same people. So it probably doesn't travel over the same links again. In other words, from a theoretic point of view, a graph theoretic point of view, it's going to use graph theoretic trails. Okay. Also, it has the property of being a physical object. It can only be in one place at one time. When it transfers from node to node, it moves. It doesn't copy, it doesn't replicate. News, by which I mean gossip, by which I mean information in general, is exactly the same. We can spread gossip and it moves from person to person. It can reach the same person many times, but typically, barring the same people that I discussed before, you don't tell the same bit of news to the same person that you did before. Well, that should at least be an error. It doesn't happen as often as the other. But one difference is that it is something which can be in more than one place at one time. So after I have it and I tell you the story, I still have it and I can still tell someone else, which changes the dynamics of things. The itinerant. I use the example of the mathematician Erdős. Right? He's a Hungarian guy. He's well known to be homeless. He shows up at a mathematician's home. He stays there for 6 months. He writes a lot of papers with the guy. And then eventually the spouse just cannot have any more of that, and they kick him out. And he goes to some other mathematician's house where he does some work. But he can never come back to a house he was at before because he's burned that bridge. Right? He's just that kind of guy. So this kind of process is one in which the form of traversal is a path. You can't reuse a node. And it's also a move. There's only one Erdős, so it can't be more than one place at one time. A virus is another mechanism that kind of looks like a path in the sense that if you have a virulent virus, maybe it kills the host after it's been there, so it can never come back to that one. Or maybe they become immune in a way such that there are diseases, of course, where you could be a carrier but not actually catch the disease. But there may be ones in which you can't even catch it. Let's see, what else have we got? A coin. A coin is one of the few examples where unrestricted walks makes a difference. There's nothing about a piece of currency that stops it from revisiting the same nodes over and over again, right? And it just keeps randomly walking through the economy. I'll skip some of these and just suggest that, well, we can summarize all of this in a 2x2 table in which we've got the different kinds of traversals, and we've got whether it's a move or a copy. And it's interesting to map existing centrality measures onto this, because to me at least, there are only two areas that here on this that are really, really important. They're the two areas that we have no centrality measures for. The spread of information, knowledge, ideas, false news, whatever, is crucial to the human condition, to what we're studying. But we have no measures for that. And the same with the epidemiological case of a virus. Of course, we can simulate it, though. We can simulate any of those things. We know what the flow regime is, and we can then find out how often something flows over a node, or what is the time until first arrival at a node. We can do that in a simulation. And I should point out that the reasons why this is not chance. The bottom row of walks, this is just mathematically very tractable. It's matrix algebra. All the Markov theory really helps here. Most of these measures are based on economic input-output methods from the turn of the last century. And then some of the graph theoretic measures that are based on geodesics, those are also easy to deal with. Now, one question that could come up is, okay, so our measures are built for walks, or they're built for geodesics, and the stuff that we care about doesn't follow either one of those flow regimes, but maybe they approximate what we need it to do, so maybe it's good enough. So let's find out what happens if we use essentially the wrong measure for the right process. I give you again marriage ties among Florentine families. And I'm going to take that as a set matrix. I'm going to drop information on any node at random. And actually, I think in this simulation, I drop it at every node, at least once. And then I let it spread according to whatever rules of the regime that I'm currently looking at. So in one regime, it could go from here to here to here to here, and it gets stuck there. In another one, it doesn't have to get stuck there. It can go back to here, it can go back to here, it can go over here, and so on. We try all different kinds. And just as a concept check, I do a simulation where things travel along shortest paths. I call this a transport or a package kind of regime. And I match it against betweenness, and you can see the exact numbers. I'm not saying that Freeman betweenness is proportional to this. It is an exact formula for the expected times that something passes over a node. Here we have many of the other different flow regimes, and we see how often, and this is for the node outcome of how often information passes over that node or reaches that node according to each of these different kinds of flows. And it's easier to look at this visually. So the map here shows the families, the 16 families as the x-axes. They've been sorted from most central to least central according to betweenness centrality, which is another way of saying that they are sorted from left to right by the amount it takes in the flow regime where things travel along shortest paths. You can see that most measures agree that the Medici are going to get a lot of stuff going their way, which ought to be convertible into something that they can exploit. And a lot of measures agree that whatever family is down here, they don't get much. But in between, there's a lot of differences. And there's particularly a really interesting difference right here in the Strozzi family. According to betweenness, they are 1, 2, 3, 4, 5, 6, the 7th ranked family, and they're the middle of the pack. According to all the other measures, this one right here, for example, it's just below number 1. They're almost the same. They're neck and neck. And what's interesting about that is if you look at the historical record, it was the Strozzi and the Medici that were fighting it out. In fact, the Strozzi were the dominant family before the Medici came along, and over a 50-year fight, Medici come out on top. But our measures should show us that, and all the measures based on these simulations do. It's the one that's based on shortest paths only and embodied in betweenness that gets the wrong answer, a misleading answer. So, one thing to do would be to develop measures that fall into some of these missing areas. I've looked already, and it's difficult to find closed form formulas for them. But really, I don't see why we need to care. Why not just simulate it? At least for smallish networks, we can just simulate the measure and use that as our centrality measure. And why do I care about an empirical study at this point? I think I know why. Just because, well, I did it with the Medici, but it was all sort of just hand-waving. Here's a real data set with real outcomes, which is a person's evaluation by their supervisor or by their peers. And I have a theoretical mechanism, and it has to do with that if you're in the midst of all the information that's the gossip of the organization, you can position yourself well so that your boss will think that you're doing a good job. Instead of saying, oh, we got to do this project that turns out that upper management has already nixed, you can get it right. So I run a little regression here, and I use betweenness, which previously is what I would have used, and I would find no results. But if I do the equivalent of betweenness with a different flow regime, where in fact things can flow along multiple paths and they don't have to be shortest paths, I find that does significantly predict an outcome. So it's an N of 1, but it's a proof of concept that sometimes doing it right gets you a significant result, where doing it badly gets you a bad result. Okay, so I do not have time for a fabulously interesting section of my talk. I'll tell you what the underlying point of that section was, though. It was that usually we have different reasons for why we want to measure the centrality of nodes, that we're going to do different things with them. So in the case of this key player stuff, I do not know how to go back apparently. Yes, okay. You might want to the key players because you want to disrupt the network by removing them, or you want to enhance the network by giving resources to the most central players, or you might want to influence the network by finding out the people who are already influential and feeding them with the proper information that they can then disseminate. There are different purposes, and it turns out that the off-the-shelf measures of centrality are not optimized for any of these purposes. And I can show this in specific graphs. So it's basically a call for using bespoke measures, measures that are designed specifically for the research occasion. And that is my conclusion. Let's see, we could just go to words. I prefer words. So basically what I've said is that in the past, we've described measures of centrality as being node importance, or we've said something like we've had some criteria, like, well, adding a tie to a node should never harm its centrality, but none of those work. None of those are really useful. I presented 3 different ways of talking about centrality measures, of saying what it is that they do, and some of them are very much overlapping, so that the involvement one and the contribution perspective induced centrality are very related, although we can find certain measures up here that cannot be done via this method, so it is not a universal description. And then also the flow outcome perspective. And having guessed that I wouldn't get to that part, I still concluded from it, and it's the conclusion that I just said, that much of what I presented here points to ways in which we can construct measures on the fly that are appropriate for our research context. And you don't have to do the stupid thing of saying, I'm using betweenness centrality because Brass 1984 used it in his seminal paper that got 1,000 citations. You could actually just do what makes sense for your study. Thank you very much. And this has never happened before, but I still had several seconds left.
Sure. So we have time for about 2 questions, if we have any from the audience.
What do you think on the axioms for centrality by Paolo Boldi?
By who?
Boldi.
Haven't seen them.
Oh, interesting.
When are they recent?
4 years ago.
40, so they're like Sabidusi kind of era. Thank you. I'll find out about those before I publish this.
Yeah, thanks for this excellent talk and your critical review of centralities. Sorry.
Who's talking? That's so much
okay.
fun. It's so great. I'm looking at this guy, but the voice seems to be...
So you kind of turned a regular centrality measure into a meta-centrality measure that measures the contribution of other people's centrality.
Yeah.
What happens if you do that again and again and again?
What an obviously great idea. I don't know. That should be tried. Are you a graduate student? Okay. Just the kind of thing that graduate students have a lot of time. They go, well, let me just run this on top of it again.
Great, so I can be flattering twice, actually. So thanks for this great talk and this critical review. So you argued that path-based centralities have the problem that they're fundamentally based on the shortest path assumption that may not be justified. But I think what you didn't discuss is that the graph also makes a transitivity assumption on the path that may not be justified in a real system. So some of the transitive path that may be in the graph may not exist in reality because they're forbidden, because there's higher order correlations, for instance.
Yeah.
Could you comment on that?
That's a good point. So my different flow regimes were very simplistic. They really all had to do with do things travel along graph theoretic trails, walks, and so on. But there is no reason why you can't have more complicated ones. So there's that result among adolescent romantic networks that shows that the X's of 2 people who are now involved with each other will not go out with each other, because it's kind of like, oh, you're a loser and you're a loser, and now we're getting together and sort of proving that we're losers. So what that creates is a forbidden loop of 4, and so that kind of flow just doesn't happen. So so it may be that we can just build in all those kinds of things. And you're probably thinking from an ergom perspective. It may be that a lot of the ergom kinds of micro-configurations could be worked into that flow kind of approach, just saying these are additional aspects of the flow regime, of what happens in this network. And it becomes... Now, the difficulty with all this, of course, I know what an editor would say. An editor would say, yes, you did so right. You built the centrality measure that was exactly right for testing your specific hypothesis. But I wonder if it would work if a standard measure that everyone else is familiar with would work. Well, I mean, what if you've just created a measure that just happens to work with yours, and you're arguing that it's very appropriate, but really it's the only measure that works. There's a real value to people to using standard methods. That's part of what we do in science. It makes everything replicable and so on. So I don't know how far we go with that, creating all kinds of odd little limitations inside of your flow regimes.
Well, thank you very much.
Okay.